Hi, I'm Muhammad Rabil Islam. Uh, in this slide, I'm showing to my final term exam solution. This is the refer figure. Question number 1. Draw the arrow according to the below condition. There is solution. First, we talk about this session. What do you mean by diffusion? Diffusion means higher concentration of electron or hole move to the lower concentration hole or electron. That's diffusion. What is drift? When we applied external bias, then in PN junction we show the drift current, or there occurs drift. Here hole diffusion, that means it's high concentration to hole moves low concentration, that's why its direction right to left. And electron also moves high concentration to low concentration. That's the flux of electron diffusion is left hand to right hand side goes. Here we know the electricity of hole diffusion is same direction of hole flux diffusion, but the diffusion current of electron is opposite due to the convention law. Electron flow or current flow only the reverse direction of electron, that's why here the diffusion current of electron, its opposite direction, this to this. Here when we applied external bias, that's its hole goes to the negative polarity and electron flux goes to the positive polarity. That's why we know about the drift kind of a hole at the same direction of hole flux direction. But when the electron direction here to here, but the current direction of drift current of electron, it's opposite here to here. In this question we discuss about draw energy band diagram for accumulation, depletion, inversion mode to be p channel using a MOSFET. First of all, we know about what is accumulation, what is inversion, what is depletion. Accumulation means when we applied positive bias in gate and source, then it's positive. Gates create a positive surge. Another silicon dioxide, another position create a negative surge. If the substrate of MOSFET is negative, that's negative silicon substrates, there a majority carrier of n-type n-type semiconductors. Electron is majority carrier, that's here is occur accumulation. But we use instead of n-type a p-type substrate, then there occurs a inversion mode due to the p-type minority carrier is electron, that's why it's here occurs inversion mode. Here if we applied more than 0 voltage in gate side, then create a positive charge, then another is depletion layer is occur by positive and negative charge. In accumulation and inversion, there got a depletion. When the gate applied voltage greater than 0, just greater than 0, there's occur accumulation uh, for n-type semiconductor, and then increase voltage. There's little bit large after accumulation, that's create a depletion layer. When we a bias voltage is increased greater than uh, uh, more greater than 0, then we face the inversion layer. In n-type semiconductor, here majority carrier is electron and minority carrier is hole. Or when hole is created under the silicon dioxide, that's here create a inversion layer, inversion mode. Here how to remove the conductive channel at VGS 0 volt. Here it's a n-type substrate, it's p positive. That means higher p-type materials here, and this is a p channel. It's gate metal, it's silicon dioxide, it's called source, it's called drain. If we VGS 0 volt, if we applied a positive voltage in gate terminal, the electron pull and increase the depletion. Here increase the depletion and will remove this conductive channel P if we applied positive bias in gate terminal. Explain the mechanism why the current show constant and saturation region. If we applied positive bias gate and source, increase voltage, that we create a depletion layer. Here is create a n channel for this VGS voltage. If we applied drain voltage here, uh, uh, if the drain voltage and gate voltage is equal, that create a saturation, and that's here create a pinch of region, because when we applied a drain voltage here, create a inversion, in this case create a inversion mode of p silicon substrate. If the VDS voltage is greater than the VGS voltage, then create a electric field, and if the VDS is more greater than VGS, then here is a large electric field, and the depletion layer between p silicon substrate and drain is large. That's why as a result the channel current flow through here to here is constant, because due to the wide depletion layer there is no current from this region. That's why the current flow is here constant. Draw the energy band graph for equilibrium and saturation mode of MOSFET. When the equilibrium mode, here this region is source region, it's called channel, and it's drain. When VGS and VDS 0, there is a VBI, built-in voltage between silicon between source and channel, and there is no current flow in equilibrium mode of MOSFET. But in saturation mode of MOSFET, here the VDS, this terminal voltage is greater than gate and source, there occurs pinch off. That's why here the current flow through the channel here create a depletion layer. Here question, why the tense conductance in saturation region is affected by uh, gate source voltage, not drain source voltage. From this equation 1, tense conductance Gm equal to the ideal saturation current by gate source current. That's why the relation between tense conductance is proportional to the IDS current. Here uh, here in MOSFET when occurs pinch off, this means VDS equal to VGS. There is, in this case, there is a white depletion layer to drain and p silicon substance. Here is more electric field. That's why here is the current flow is constant. If after a pinch off, if we increase VDS voltage but current is constant, that's why VD is not responsible for uh, current in this case, but if we increase VGS voltage, that current is increase. So in MOSFET VDS voltage is not affected the tense conductance in saturation region. What is the difference between acceptor like state and acceptor level? Here this MOSFET, it's metal side gate and gate dielectric or gate oxide. Here mention this is channel. When we applied bias, here in built-in here create a interface steps as a defect. If this interface traps a defect, receive electron dispersion is called donor like state, and it's empty, then it's called acceptor like state. Here question is acceptor like state. Acceptor like state is not contribution to flow current, rather than it's a bad for MOSFET. But acceptor level in p-type ionized acceptor, electron move from to here to here. In acceptor level, electron field, but here a positive charge. In this way, the electron contribute to flow current in a semiconductor. It's a help to flow. It's help to flow current in a semiconductor. Here is a difference. If acceptor like stage is bad for MOSFET, but acceptor level is good for semiconductor. Explain the degradation mechanism of MOSFET under positive VGS stress. When we apply negative VGS, at this time the VDS is 0. We think in metal gate in position gate position, here is minus electron, here it's a metal oxide, and channel generates induced 10 electron. in initially in device, but as some days we applied negative VGS that generates here minus uh, 10 electron, but in the channel side induced 6 electron, but where go the another 4 electrons that's absorbed by the metal oxide. Now in this way the same, that's why here after that the VTI is negative shift when operating MOSFET device degradation. Here the IDS and its VGS. Initially its conduct is good, but few days after their IDS value is degrade. If we apply a positive VGS in MOSFET for stress bias, accumulated electron from N channel, here 10 electron, here is positive charge, here same amount of negative charge here, but few days after here reduced the negative charge. The another 4 charge is moves to the silicon dioxide layer in positive bias stress for N channel. After that, a threshold positive shift when operating in MOSFET device degradation. Here it's IDS current and its VGS when VDS is 0. First of all, when we apply positive tensors and we get from N channel negative tensors, the curve is here, but after degradation of MOSFET we generate here positive 10, but we induced here negative 6. Another 4 is accumulated by the silicon dioxide. That's why the curve is degradation. Why is the hot carrier effect for hole less serious? First of all, what is hot carrier? In short channel device, the high electric field near the metal dioxide substrate interface, another interface, substrate oxide interface, electron or holes, and they cross the substrate interface to the enter the oxide layer. Here the barrier for electron silicon dioxide gate 3.1 electron volt, barrier for hole silicon dioxide gate oxide 5 electron volt. In this case for less serious, for hole less serious, because silicon dioxide less impact interface of hole, because of silicon dioxide band gap is 5 electron volt. Explain what causes threshold voltage role of phenomena. The channel length reduction reduce the threshold of MOSFET. This phenomena is called threshold voltage roll-off. If in a short channel device, if the drain and source depletion razor further into channel length, depleting a part of channel, in this way a laser gate voltage is required to invert the channel, reducing the threshold volt. In this case, drain voltage is more higher. This is the cause of threshold voltage roll off phenomenon. Explain the mechanism of low threshold voltage in terms of charge sharing. The threshold volt of MOSFET device reduce due to the channel length reduction or short channel. In short channel device, the drain and source depletion region enter further into the channel length and depleting a part of channel. If the channel length is reduced, the threshold volt goes to the negative direction. This here, in negative direction, the doping concentration is more high. Here, the source positive negative is create a depletion layer, create depletion layer. If the channel length is short, the VT shift negative. That means there wide range of depletion layer between drain and substrate of MOSFET. If threshold voltage become low and negative threshold volt, what is going on for the MOSFET? Describe the problems. If the threshold voltage decrease, the substrate concentration is rises and thickness of oxide layer decrease. We face the problem. Substrate concentration rises and the oxide layer decrease. That's why there is more defect we faces in MOSFET. How to reduce the hot carrier effect and DIBL. Here, lightly doped drain is a solution to reduce hot electron degradation. Additionally, lightly doped region in source drain region makes depletion wide at reverse bias drain channel junction and reduce electric field. Here, if we lightly drop drain here we lightly dropped here a n-type materials. That's why here it create a depletion layer, but here reduction the electric field. That's why the effect of hot electron is reduced in this case. How to reduce DIBL? In this portion, implantation through gate. In a p-type body, here we implantation a p-type materials. There's a hollow, there's called pocket doped region using the method of implantation. If there is no implantation but without halo, that's mean there is no implantation, the channel is too short, that's called short channel. There is some disadvantage of short channel. If we applied the implantation technology, here use a p-type substrate, p-type materials, here, then the channel length is increased. That's why if we introduce halo implants, it's improve the performance, suppress some short channel effect, and the overall performance is good in MOSFET. What are the pros and cons of LDD and halo? LDD for reduced hot electron degradation, LED con fabrication complexity, drain resistance. Halo pro reduce the drain-induced barrier lowering, halocon, increase channel length. Describe my expression for this class. First of all, grateful to the professor to hire a semiconductor pioneer who conducts a course that's named Semiconductor Physics and Electronic Engineering to teach the physical meaning of semiconductor basic and MOSFET. Uh, Overall, I find this professor pleasant demeanor and punctuality that makes me mesmerizing. The teaching style is more favorable for the student. Professor tries his best to teach us properly and recap the previous class. Even professor use his body language to understand us on the hard topics. First to the last class, I try understand properly and more clearly. In conclusion, I enjoy this class more with professor and my classmate. Oh, what's the takeaway for this course? Honestly speaking, this lecture helps to me understand the semiconductor definition and identify the N-type, P-type from the band gap figure easily. I perfectly understand the secret of Fermi direct distribution with various temperature. I learned more from this course. Fermi level is the mathematical guideline which is imaginary line. The conduction band and valence band is not a mathematical guideline or imaginary guideline. It's a physical energy level. And I also learn Fermi direct distribution function probability for intrinsic semiconductor, for extrinsic semiconductor. I also learned the relation between Fermi distribution, temperature in various temperature, the relation between Fermi distribution probability, energy level in equilibrium temperature. How to doping process of N-type and P-type semiconductor with impurities. Also, how to select the impurity based on energy level of the impurities table provided by professor. A depletion layer mechanism of PN junction. I also learned from this lecture how to make compensate silicon. Basic operation of MOSFET. How to occur pins of inside the MOSFET. Overall, in my calculation, at a time I think that enables to me teach other about semiconductor and MOSFET more confidently. That cannot mm, that cannot uh, before this class.